Welcome to Wireless Future. I'm Eric Larsson, and I'm here as always with my colleague Emil Björnsson. Hello, Emil. How is Stockholm today?
It's a great sunny day here. How is Linköping?
Oh, it's also great. A little bit of snow, like a millimeter or so on the lawn, above freezing, slightly above freezing, I think. Today we have a guest from Aalborg, Petar Popovski, Professor of Wireless Communications, Fellow of the IEEE, Vilum Investigator. Hello, Petar. How is Aalborg this morning?
Hello. I think following up, I think it's also sunny, and it seems that Sweden has been following us in lifting the restrictions and coming back to normality these days, right?
That's great indeed, and we all look very much forward to that, I think, after something like nearly 2 years of the COVID pandemics.
Exactly.
Yeah.
Amazing. Wow. So Petar is a long-standing friend and collaborator, and is also an expert on wireless communications, particularly on MAC layer technology for 4G, 5G, and 6G. He's also an author, a prolific author of papers, and also of a recent textbook that just came out. I see that, Emil, you're sitting with it.
Yes.
Maybe you could hold it up for display. Wireless Connectivity, an intuitive and fundamental guide. So this is a text that I'm also a proud owner of a copy, which unfortunately I forgot in my office. I'm right now in the recording studio, obviously. So this is a nice book, I think, that targets maybe not the layman really, but it's really a soft introduction to the topic of wireless. And one thing I like in particular in the book are the illustrations, which really, I think, cater to the young generation indeed. One of my daughters just turned a teenager. She started to read the book, and then she came back after 2 pages and said, "Daddy, what is duplexing?" And I think that's really sending the touch here. So today, Petar, we are going to talk with you about a term and a technology that goes into, I believe, at least partly into 5G, and that is ultra reliable, low latency communications, or URLLC for short. So I think to start this off, I'd like to hear your view and explanations on the terms themselves. I mean, to the layman, it might seem that reliability and latency are really the same thing, right? I mean, you could take reliability to mean that, you just get your data in time with low latency or low or no delay. Still, it seems that the technical definition of these two terms, reliability and latency, are different. So how is that?
Yeah, thank you, Eric and Emil, first for having me at your podcast, which I think it's a very, very important input to our research community and to the engineering community of wireless. A very unique and very timely effort, and I'm happy to be guest on it and talk about the topic I talked for a relatively long time on. This is ultra reliable, low latency communication, and as Eric says, it has 2 elements there. There is a reliability and latency. And when I was thinking about this question, which Eric and Emil sent it to me earlier this week, I find it deceptively simple because it's normally, to a communication engineer, reliability and latency are clearly distinguished. But here the question is that somebody would expect latency things to happen instantaneously and just to happen deterministically, right? So let me try to unpack it. Ideal communication would mean that things are happening instantaneously. So we are basically transmitting the information from one point to another instantaneously and perfectly. Then if we now take a step back and look into the fundamentals of physics, and let's say even the relativity theory of Einstein, we have the horizon of events, right? So things do not happen instantaneously. We need some propagation time to for things to happen. So we can say, okay, if we adopt the framework of the special theory of relativity, we say there is some time that needs to pass for things to happen, but it's the event is reproduced ideally. If you remember in Einstein's thought experiments, there are these lightings and so on which are reproduced ideally after certain seconds, and that is the physical delay imposed by the propagation. And then now let's take Einstein's experiments of light propagating and taking time to propagate, which is kind of carrying the latency, and assume that a random blockage occurs on the light. Then this means that the information may not be transmitted perfectly, right? So it might happen that with some probability we do not reach that event horizon, even if the light is telling us that we should reach it deterministically. That's the reliability part, right? So if we combine the reliability and latency, then we are arriving to a description of an event in a statistical way that is going to happen within a certain time, right? So the reliability is referring to the statistical nature of it, and latency is referring to the fact that it takes time. Still staying with the Einstein experiment, I think it's very interesting to see that what he assumed in his thought experiments was that we have infinite rate transmission of information, right? Because the light is just being reflected, so it carries information about the entities from which it's reflected, and it's ideally reproduced at the other side. In communication, in the digital world, we have a certain limited data rate. So instead of just saying that the event is propagating within a given time and with certain reliability, we also have to add what is the rate that is required for that event. So suddenly this digital world has more parameters than these thought experiments that were used in theory of relativity.
So what you're saying is that there is always going to be a latency because of this physics, and reliability refers rather to like what is the probability that we can guarantee a particular latency target. Is that a correct assessment of the terms?
That is a correct, but I would say that's a very basic latency because again, coming back to the theory of relativity experiments, we never speak about the processing time at the observer. And that processing time at the observer for reproducing the information is also going to take time. And actually, it is a dominant time, maybe in the latency, when we have a decompression of a video, playing out of a video, and so on. So I like to think within this framework of physics, of the theory of relativity. But the interesting thing is that in the digital world, we are adding up points which do not exist in the original thought experiment. So we also know, for example, from a basic communication theory that we do some form of a block coding. So we do not just send every bit as it comes. So we do some coding. And then when we transmit it, we have to use some time to reconstruct information from that code. And all this gets additional latency on top of the propagation latency.
Yeah, so the processing will add to the actual physical transmission time. I think that's something we might be returning to. It seems like an important distinction. What do you think, Emil?
Yeah, definitely. So, of course, reliability and latency have been important things in wireless all along. I suppose the new thing here is that it's ultra reliable and particularly low latency. So, in what use cases do we need to go beyond the reliability and latency that we have in previous networks? And do we always need that? Can we sometimes get away with only low latency or only high reliability? Or
I think that the idea of having very high reliability for wireless comes from the fact that we have started to build networked cyber physical systems with cables, and they were working, quite reliably, but they lacked the flexibility of recomposing moving parts and so on. So we say, can we do that with wireless? In a sense that ultra reliable wireless is expression of a desire to achieve with wireless what basically has been achieved by cables. So the question is, can we have this wireless connection which is active almost all the time? And I would say that any real-time system where we need that things happen with high reliability within a certain short time window could be benefiting from the ultra reliable low latency communication. On the other hand, if we look how we have designed our communication systems, we say that we have, for example, a part for computation, part for compression, and then part for transmission, and so on. So we have these chains of modules within the system. And then let's call this a layered system, as a layered design. Then what we would say is that if we make a block of wireless connectivity, which is offering very high reliability and low latency, then we can use this as a building block to build something else, right? And in some sense, putting very stringent latency and reliability requirements on the wireless is a result of layering. Is part of this. I like to call this high reliability and low latency a victim of layering, because once we separate them into a block that offers such a high performance, then we can use it as a building block into something else. The other question is, if we are aware about the actual requirement of the application in a given set, do we need to have such a stringent latency and reliability requirement? And this refers to something that for a long time has been called cross-layer optimization or coupling of the layers. And I think the interesting question in that sense is when you say, I want to deliver this packet with reliability 99.99% within 1 or 2 milliseconds, the interesting question there is, what happens if you do not do that? And the point is that there is some system, there is certain safety measure within the system, or there are some other ways in which the system can absorb these types of failures. The question is, what is the cost of these failures when they happen? And that's why we have to look, let's say, holistically within the whole application in order to understand whether sometimes we can relax this requirement. For example, if we require only latency, let's try to decouple them. If we just have a low latency, that means that we do not give statistical guarantee that the packets will be delivered with high probability. This means that we have other means. For example, there could be a predictive model, some machine learning method, or some other methods which, upon lost packets, they're trying to compensate for them. But otherwise, when the packets are arriving well, they're arriving with very low latency. If we look only with the reliability, then we have a different type of system design where we say, okay, within some relatively large latency, we have highly reliably an input coming. Then let's align our systems to these longer term updates so that our system can operate reliably. And again, we are going to use certain models and machine learning to compensate for the time lost or for let's say for the missing arrival of a packet.
Mm-hmm. Yeah, so I mean, it seems to me that the difficult thing here is really to get reliability and low latency at the same time, right? I mean, you could think of like it's easy to get reliability in a way that you just keep sending, keep repeating your data until it reaches the recipient, and eventually that should happen, right? I mean, if you just add enough repetition coding, use enough power spread over enough time and bandwidth and so forth. At the same time, you could also achieve low latency if you don't care about reliability. Just ship off your data, and there's going to be some minimum latency time, presumably because of propagation delays and because of processing and so forth. But the really difficult thing is to get both at the same time. Do you agree with that? And I mean, could you point a little bit to like the technical challenges involved in achieving latency or low latency and high reliability simultaneously?
Yeah, I think this brings us to the very basic communication theory and the communication model of Shannon. Because before 1948, let's say before he started the area of information theory and made a mathematical theory of communication, I believe there was a pervading thought that by sufficient that you need to add a sufficient diversity, repetition, and so on towards infinity in order to achieve reliability, but that would bring your rate to be zero because you're going to repeat the same data. I think it's instructive to look into Shannon's communication model.
Well,
we
Peter,
talk about,
I think really when I said repeating, I meant like, well, keep on adding more and more parity bits and so forth.
Yeah,
but
that's what I mean.
Maybe that's what you're after here. So
yeah, that's what I'm after. So let's take the communication model where we have let's say a single use of a channel, a single transmission, right? First, let me say that in Shannon's model, there is no time specified. There is only causal relationship between the channel uses, how we go one by one, right? And if we want to achieve low latency, then what we would do is we would take the data and just send it over that channel. But that's automatically not reliable because we are left with the reliability of the channel as it defined by nature. On the other hand, what Shannon is saying is saying, look, you have to not use the channel one time, but you have to take your data, encode it, and use it multiple times. And the more you encode the data, then the better reliability you are going to achieve, provided your rate is under certain value. This is clearly illustrating the trade-off between reliability and latency, right? Because if we assume that channel uses are taking a specific time, as I said, periodically, that means that the more you wait to do this encoding, the more you collect the data and make longer blocks, the higher the reliability that you can achieve. So this is even mathematically captured.
It's there, indeed.
It's there, yes.
Yes. Yeah, it's a nice illustration, I think, of the, say, technical relationship between these two terms, right? Latency in terms of when do you actually send the bit versus when can you decode it reliably, and reliability in terms of the, well, probability of error that it actually arrives correctly within the time window.
So you said a number before, which one can also find in many places when it comes to reliability goals here, 99.9999. I guess it's 5 nines, or should it be 4 or 6? Where does this number really come from?
I mean, there is, there are multiple numbers of reliability which are floating around in different areas. There is also this 6 sigma, right, where we look into the 6 sigma spread of processes and so on. And 99.999% is if you look into that's a digital systems or any system which is running and has to be maintained with high reliability. So 5 nines would mean that the system is down around 5 minutes per year. So that would correspond to that. So this is where the number is coming from. And the interesting thing is that when you are doing this, for example, for data center, then this 99.999% is referring to all the things there, which is the storage, the power supply, and all the elements which are connected to the functioning of the data center. The sum of all of them, or let's say the product of all of them, should lead to reliability of 99.999%. And I think it was this number is kind of a symbol of high reliability within that's a digital system. So I think it was adopted early on within the ultra reliable low latency wireless. The thing is that again, this number is only for the block of the wireless link, and even for the one-way transmission of it. And if we want to look into the overall end-to-end performance, there are other blocks that we have to add there, and adding more blocks is going just to decrease the reliability.
I see. So another thing you were mentioning earlier was diversity, that we need to sort of, for example, spread the data over time and bandwidth in order to get some more reliability. Are there other types of diversity that we can utilize to achieve reliability, and do they sort of help in the same way, or are they sort of complementary in some way?
Yeah, sure. So if we take the theoretical case of very low latency and reliability that goes to 1, that means that we just have to use an infinite bandwidth, right? So if we use infinite bandwidth, then in principle, we have perfect reliability and very low latency. Now, of course, the reliability and latency should come at a certain constraint. power, of bandwidth, and so on. And so we cannot use infinite bandwidth, but obviously if we increase the bandwidth where we do our transmission, we are going to get a level of diversity. And then especially in wireless communication, when we have frequency selective channels, so this is going to give a diversity and statistical independence of different transmissions that could lead to very high reliability. Another level of diversity is a spatial one, and you both are primary experts in the area of massive MIMO, and you could also say it in the same way I said for the bandwidth. Okay, if you increase the bandwidth to infinity, then you get perfect reliability. Then you could say if you increase the number of antennas to infinity, you get perfect reliability. It's not in the same way as with the bandwidth, right? Because in the case of multiple antennas, we are not the way in which we are getting diversity is different from the one that we are getting with bandwidth, right? Even if we have again infinite degrees of freedom theoretically. So, but this also says that the obvious candidate for adding diversity is a spatial diversity and multiple antennas. But as we all know, using those is involved with certain overhead estimation and so on. So it's not always easy to keep the low latency. So there is another challenge where we have latency reliability challenge with respect to multiple antennas, estimating and using them. And another one is, which is always useful, is a two-way retransmission and ARQ processes. So because we tend to think, especially if we are closer to the physical layer, we tend to think about one-way transmissions. But eventually the systems require two-way transmission where we have acknowledgement and confirmation of reliability and so on. In that sense, we can use ARQ processes. The problem with the ARQ is that it consumes time because the acknowledgement has to be causally related to the previous transmission. So we have these steps are taking place in time, and this is how we are eating up the latency budget. So we have to be careful with using this degree of freedom. Finally, if we go at the higher layers, we also have the opportunity to use multiple interfaces to transmit our data, and that is going to lead to some form of interface diversity.
So diversity is really a key here, right? I mean, in order to combat the wireless fading, which might be the most important culprit when it comes to achieving highly reliable communication. It still seems to me, I mean, I understand the spatial aspect that you add more antennas and you get spatial diversity, which improves your reliability correspondingly, and you increase your bandwidth, then you'll expose your signal to more and more independent realizations of the fading in the frequency domain, right? Although the power that you spend is also spread over a larger bandwidth, so the trade-off at some point isn't maybe entirely obvious. And ARQ or time diversity is a little bit maybe less convincing, because if the goal is to cut on latency, you don't want to keep on like retransmitting and sending ACK and ACK bits back and forth and so on. So I think I'd like to return to this question that Emil posed with numbers, and it seems like a useful rule of thumb to remember that 99.59% reliability corresponds to 5 minutes of outage during 1 year. And that might certainly be fine, I mean, in certain applications, but you could also argue that, like, well, I mean, if this is like a video game or a social media app or something, then 5 minutes is actually not much, right? You probably could live with like half an hour of outage or something else. But on the other hand, if it is a control algorithm in a nuclear power plant, then, you know, I don't want a 5 minute outage per year there. So it still seems to me that is 59% reliability is a very arbitrary number that's, you know, just you came up with it over a cup of coffee or a beer or something, and then you put it there as a kind of de facto standard for what wireless transmission is targeting, right? Correct me if I'm wrong. In any case,
that's correct. That's correct. It's over a cup of coffee or a glass of wine, even more.
Yeah, so continuing on the theme of numbers, then another figure that seems to pop up here and there in terms of latency requirements is 1 millisecond. So why that number? I mean, why 1 millisecond?
That is also might be related to the same cup of coffee you were mentioning before, because I think the original requirement which was posed for URLC in 3GPP was to send 32 bytes within 1 millisecond with the reliability 10 to the minus 5, which is basically 5.9. If I go back in the early days of one of the first big 5G projects we were doing back in 2012 and 13, so I was in charge there in the project to define the requirements for ultra reliability and low latency. And what I thought was that we need to define short-term reliability, which is URLC today, and long-term reliability, which is kind of more relaxed latency requirement, but also still high reliability. And then there was a big project at that time with telecom operators and so on. So what I did is I interviewed them and tried to find where is the border between low and short term and long term, so low latency and higher latency, and it turned out to be 10 milliseconds at that time. And then I saw the number of 1 millisecond within the 3GPP. But then in the meantime, this number has been developed into various numbers because not every application requires 1 millisecond. And then if you look, for example, the Open RAN specification, they are dividing the timing process into real time, less than 10 milliseconds, near real time, between 10 and 100 milliseconds, and non-real time in seconds. Then you have this association 5G ICA, which is for industrial automation and control, for using a 5G within that context. They're defining hard real time, which is microseconds even, and milliseconds. Then there is soft real time, which is on the order of second, and non-real time, which is multiple seconds, right? So there is some more relaxation there. So if you see some of the latest releases of 3GPP, they're also doing segmentation depending on applications. There's, for example, process automation that requires tens of milliseconds. Then there is a factory automation, which requires from 0.5 to 2 milliseconds and so on. So this is saying to me that there are going to be certain coupling, certain cross-layering with the upper layers where we're passing parameters and trying to satisfy the timing requirements depending on the application. And what we have tried with my group is to write a consolidated paper on the question of time within wireless communications as we are moving towards 6G. And because there are also other timing measures like age of information, freshness, and so on. There is a two-way latency. So I think the consistent way to look within timing and reliability is the following: to say we need within these communication systems to have two different types of statistical process, either statistical decision or statistical estimation, as we do in all statistical signal processing problems. So the question is, this statistical estimation or statistical decision is taking place within a certain time frame. So we would like within a certain time frame to achieve certain correctness of the estimation, or that some event happens with certain reliability, and then we are putting this in a perspective of time. Using that perspective, which is general, then we can accommodate various reliability and latency requirements.
Yeah, absolutely. I mean, so referring to like the number 1 millisecond. So one argument I heard, I think some time back, was that 1 millisecond is the time that where a human can notice a delay. Like, for example, a musician who might be plucking a guitar string, and then if you introduce a delay between that plucking of the string and what you actually hear if you're wearing like earphones, then if that delay exceeds a millisecond, then you would notice that there is something wrong. I'm not sure if that's accurate or not, but I suppose one could relate numbers of this sort, like a millisecond, to actual experience of humans, at least for applications where humans are the end users of the system, right?
Yes, but in the example that you are giving for the musician, we should also take into account that there is a delay of audio processing and so on. So I think if it's a millisecond for that, then we have to probably add the other one. On the other hand, I saw numbers like for a visual input, for a picture is registered if it is seen for longer than 13 milliseconds.
13, okay. Yeah, interesting. That's good to know. So, but I mean, staying with the physics, 1 millisecond is actually quite a long time, right? I mean, light travels this much, like 30 centimeters in a nanosecond. So 1 meter takes 3 nanoseconds, 1 kilometer takes, 3 microseconds, and something like 1,000 kilometers takes 3 milliseconds then, right? So in a millisecond you can get very far. So in terms of the actual propagation delay of the electromagnetic waves, then a millisecond is a very long time. So I mean, do you agree? So the main components of the latency are, for most systems elsewhere, I mean, excluding like satellite links and so forth that go like halfway around the globe, then the actual propagation of the wireless EM waves is a very small part of this millisecond latency.
I totally agree. So the latency is elsewhere there. So because if we are looking into let's say factory floor automation, then we are within a distance of meters, right? And according to this,
nanoseconds
delay,
more or less,
nanoseconds. So it doesn't really matter. What really matters is the processing and the communication the delay there. So what I think is that there are multiple elements there. So if we think, for example, of the let's take compression. So we have the compression takes time. So if we want to do the compression, then we are getting a lower rate. The better we do the compression, the lower the rate we are getting. But the compression is going to take time. So we are going to eat up the latency budget. Then we are getting a low rate, and this low rate is easier to transmit with a higher reliability. But wait, we have eaten the latency budget by the compression, so we have less time to transmit the signal. And plus, there are issues when we go to very low latency. There are, of course, issues with the real-time operating systems and how the controllers are made, because there are certain read and write processes there that do not happen instantaneously, right? There is a reading system within the controller that is, fetching the data, sending, and so on. So all this adds up to a latency where the propagation latency, as you mentioned, is negligible.
Is negligible in most cases, yeah. So this, I think, is a very important point that you're highlighting, that the propagation delay itself is nearly negligible. I mean, I think we said earlier, right, the kilometer corresponds to, we say, 3 microseconds, which is nothing, right? But it might be other delays on the physical layer, though. I mean, I'm thinking of like in NR, isn't it like an OFDM symbol is something like 70, give or take a few, I guess, but microseconds, that's not much. On the other hand, you probably want like a frame with at least a couple of OFDM symbols on uplink and then a couple on downlink, and then you need to switch in between, at least for TDD operation, there needs to be a switch, right, from uplink to downlink. And then if latency, or if the transmission includes both an uplink and the downlink component, then that switching time is just going to be there, and the OFDM symbol duration is just going to be there as well. So there might be like other things than the sheer distance it takes for the wave to propagate. Yeah, interesting.
But this is a very interesting point you're highlighting, Eric, because what you're saying is that the format of a synchronous system, like we have with the frame and so on, the very format of a synchronous system is adding its own delays because you have to wait for your turn and so on. And we can think that the same happens maybe within the device where we have certain process of reading and writing of real time and so on. And in that sense, I think it becomes interesting to look into alternative processing systems which are asynchronous, like the neuromorphic and so on, where things happen.
Yeah,
not
or we
we
just go back to analog, right? So we scrap all these buffers and all decoders and what else, like algorithms that take time to iterate and need to store lots of data, and what do you say, Emil? Any thoughts?
So obviously we can't change the speed of light, and it's already moving fast enough, I suppose. But if you think just from a deployment perspective, if there is a base station 500 meters away, and you have the opportunity of deploying a small cell in your factory or where you are, so you would then, of course, shorten the distance for the propagation. Is it worth it in order to sort of get better reliability and latency?
Based on the calculations, quick calculations Eric was doing, probably not. Probably we have to harvest the lower latency elsewhere, and I think the idea of analog transmission is really good. To go towards that, we have to go a step back and say, why did we use digital transmission? I think there are at least two major reasons. One is the regenerative nature of it, that we want to have a perfect reproduction of it. And second is the easy integration of data and metadata, right? Because we can put this metadata that is explaining what the data is about, and based on that, we can interpret the data. In the analog case, when we are getting something, we do not know about its integrity, right? So we do not have the CRC check really on it. We have to have some analog domain constraint and so on, which would still be a coding and still a latency, right? So if we want to have this integrity. But I think the idea of having the metadata being sent digitally, because it's a discrete set, and the other data being sent in an analog way, could be interesting. And I think this is happening within 6G in a sense that we are looking into a combination of communication and sensing. Well, sensing is some form of analog data that we are not controlling. The question is, how do we integrate that within the synthetic data that we are sending over a communication link, right? So the point is whether we could find the architecture of signaling and metadata to integrate these types of information.
Yeah, I agree, and I think also that the case for deploying a small cell to improve your LLC performance would not really be about sort of shortening the propagation distance, but perhaps improve the communication channel in other ways, like more line of sight or less obstacles in between.
Or more predictable channel, that if you can find it.
So if we look at, like, I don't know, from a more fundamental perspective at the future, then suppose we were to scrap not everything we know, but everything like we have built, right? Like standards and so forth, and design a new communication standard for wireless from a clean sheet that would support ultra reliable and low latency communications. How would that differ? What components would go in there that aren't currently like in 5G or maybe 4G, but let's talk 5G. Could you shed some light on that? I mean, what would be the new technology components that we would have to throw in there in order to really achieve these 5 nanometer goals and this millisecond and all that we talked about?
Yeah, I think first of all, with the systems that are working already, the standardized systems and so on, we have to be very careful with revising them, because these systems contain wisdom of a lot of practitioners and people that have implemented these systems and so on. So it's easy to say I have this very nice idea about transmission, but then you figure out that you need signaling, and then for that signaling you need something else and so on, and suddenly the advantage of your technique disappears. I think we have seen something with COMP, coordinated multipoint, where it looks great that you have these distributed antennas, but the signaling between them and the outdated channel state information and so on was not really helping to achieve that performance. So in some sense, I think we need to look what we could revise and I think 3GPP is already doing this. For example, redefining the frame so that we can have a faster switching between uplink and downlink to have ARQ processes. Then we have grant-free access. I think, in my opinion, understanding better how to enable two-way communication could be one of the key points here. Because think that the way we are doing two-way communication is practically always in the following way: that you send some data, and then you get a single bit acknowledgement or not acknowledgement, and then based on that you iterate based on incremental redundancy. What happens if you put certain machine learning or certain predictors at both sides that are trying to figure out what is happening with the transmission, and then maybe sending a different type of feedback, right?
Yeah, that's an interesting thought. What do you say, Emil?
Yeah, I was starting to think about that, of course, if we do ultra-reliable low-latency communication, we will sacrifice something like data rate. And there are more than one service that people are talking about when it comes to 5G, with this being one of them. In episode 26, I think, I was talking about network slicing, and usually when people are saying, 5G should support different services through network slicing, they like to talk about end-to-end slicing or some kind of isolated slicing. You take your physical network, you divide up into really isolated parts, one for ultra-reliable communications, one for mobile broadband, and maybe one for something else. But I've seen that you have been working on some kind of non-isolated, non-orthogonal type of network slicing, where I guess the reason for making them really orthogonal to each other is that they will not interfere. So we just slice up the resources, and then each system can be optimized on their own. But what would be the benefits of having multiple services in a network and still letting them be non-orthogonally implemented?
So I think the key word here that you mentioned was that they should not interfere. I think the way, if we take it a more general view on that, is not that the system should not interfere in terms of wireless signal, but they should not interfere in terms of performance. And then once we go to that level, we say, what are the other options? Can we mix the signal within the wireless domain? So let's see, for example, the excitement that our community has about NOMA, non-orthogonal multiple access, and let's say rate splitting or similar techniques. These techniques are known in the information theoretic community since the 70s, right? I mean, the multiple access channel, the main result, one of the main results in the multiple access channel is that we should allow the signals to interfere to increase the overall some capacity or to reach some points of the capacity region which are not reachable with orthogonal transmission. And then the question we asked there was, can we mix the signals and still achieve the desired performance level? And the motivation here was what we call the reliability diversity, in the sense that if you say that ultra-reliable low-latency communications requires 10 to the minus 5, and then you have the broadband communication that requires error probability of 10 to the minus 2 or 10 to the minus 3, this is 2 or 3 orders of magnitudes of different. That means that the broadband will regard the ultra-reliable as a perfectly reliable one, because it's just three orders of magnitude better. And the question is, so it's the same way, let's say it is the same way in which somebody that designs, let's say, a MIMO system, and then you're going towards a channel estimation procedure, your favorite beamforming, and so on. But what you assume all the time is that the reliability of the underlying hardware is 100%. You don't think about it, because that's, and the reason for that is that it's a couple of orders of magnitude larger than the system that you're observing, right? So that's why you are ignoring that. So the point is that, can we benefit from observing this difference in terms of reliability with several orders of magnitude? And that leads to some interesting possibilities for mixing wireless signals, let's say URLC and EMBB and so on. So for example, one can say you should never mix the ultra reliable low latency communication with the broadband, but you're given a limited spectrum chunk, so we'd like to use it as much as possible. So if you have very sporadic ultra reliable requests, then most of the time your spectrum will stay unused. It's like the military spectrum, which is highly reliable, but perhaps not used all the time. And on the other hand, if you use the spectrum for broadband, then you should not put very high rate, because from time to time it can be interrupted by ultra reliable low latency transmission. So the point here was that if I design the system to work for ultra reliable low latency transmission and I ensure some reliability, then this could be observed as perfectly reliable by the next service of the diversity, and then we can design that level of service.
Yeah, so are you suggesting, like, even with network slicing and different owners of different pieces of spectrum and so forth, you could still, I mean, when a packet comes that's really critical, that really has to arrive right now, and with all this 5.9 reliability and so forth, and the system is just irrespective of what's going on in this different frequency or slices of the spectrum, just transmit it all over everywhere, and just tell everyone else in the network to shut up, and then send this packet and get it through. So in that respect, like, interweaving also, irrespective of how the network and how the spectrum is sliced, then use all the resources that are physically available to transmit when it's critical.
It's in principle, if you design your critical system to account for the underlying interference, then you use as many resources as you can. But keeping in mind that if you're able to decode that system with high reliability, that means that you can remove it using successive interference cancellation, and for the remaining system, the system looks clean without any interference, right?
Yeah, I see. So rather sending something and then using that something as decode it everywhere and subtract it off, so that the fact that it interferes doesn't make a difference, or isn't really doesn't really constitute an impairment in the end.
Exactly, and plus keep in mind that there is an interesting relationship with latency and reliability. Is that if you go with if you design the system to be able to decode the highly reliable and low latency service, then the systems with relaxed latency and relaxed reliability can wait for some times until the interference is cancelled, and then decode the rest with certain reliability.
Yeah, I see. Interesting concept indeed. So maybe staying on this line of thought, different protocols. I mean, I think you mentioned earlier grant-free as one technology, grant-free random access as one technology that would or should maybe enter, well, future generations of standards that are to support your LLC. Will this be the one? I mean, grant-free access, will that be a deal breaker, you think, or are there other types of technology in the random access protocols that will be game changers eventually?
I think the how it's called, the grant-free is definitely removing some of the grant-free is definitely removing some of the delay, but it's putting challenge in terms of reliability, because when it's grant-free, it means that we have not prepared the field for our clean transmission, right? Because if you are granted transmission, then it means that you have the medium with high reliability. And on the other hand, I think the generalization of grant-free concept is to say that we decrease the number of steps in the access for getting access to the medium. For example, if you see in the LTE, I think there were 12 steps, including some authentication to arrive to the actual transmission from an unconnected state, and this has been decreased Of course, the people in 3GPP found out ways to decrease this and to make a lighter access procedure and so on. On the other hand, if we look into sporadic transmissions, which have to be reliable and secure as well, so we need to have certain pre-authentication, pre-identification. So we have to count this after for example, the secret keys have been exchanged and so on. And again, the role of machine learning there would be to try to predict the states of the devices that are accessing, and based on that, decode the information that is coming. Because we can think of the protocol information, of the control information that is kind of trying to tell to the destination what is the state machine of the state machine of the state of the state machine of the transmitter, and trying to change the state machine of the receiver, right? Because we are having, let's say that we are in a state of establishing the connection. So we are sending our message, we tell what is our identity, maybe we say how much bandwidth we want and so on. Then after that, we have to transfer to another connected state. And this transferring between states is basically exchange of control information.
Yeah, so...
Yeah. Let's switch topic a little bit here, and I was thinking about frequency bands, because in 5G we are sort of really expanding what frequency bands we're using. I guess many of the first deployments of 5G is in the 3 gigahertz bands, but then there are the intention of taking the 3G, 4G bands maybe below 1 gigahertz, use them for 5G eventually, and also to deploy new smaller cells using millimeter wave spectrum. And different types of spectrum have different kind of characteristics. Some might be more reliable than others in terms of the fading characteristics, but some are also providing more bandwidth than others, which I suppose is a good thing for reliability. So if you have to choose a certain frequency band to deploy new URLLC services, what band would it be?
This is a difficult one. The point at the lower bands, as we know, is that they are propagating longer. But that means that if there is a longer propagation, then you have a more unpredictability of the environment, because there are more random factors in the environment that are affecting the final, how the signal looks finally, right? So there are multiple scatterers, multiple, diffraction and other reflectors and so on. And as we all know, the reason that the higher frequencies that do not have so large range as lower frequencies is not the free space propagation. In free space, all the frequencies propagate in the same way. That's not the point. The point is that they are affected by these scatterers, reflectors, absorption. They're affected differently by these frequencies, and of course the diffraction, because while the longer wavelengths can go around some obstacle, the shorter are blocked by it, right? And so in that sense, that we have at the lower frequencies that we have a larger range. So we can support this communication over a larger range, but we have more unpredictable factors from the environment that are affecting it. On the other hand, as we go to the higher frequencies, then we have some form of an on-off behavior, that the range is shorter and the beam is either there or is not, or is blocked or is not. So, and this is extreme, I would say, in terahertz frequencies, which are now popular for towards 6G. So the point is that when we have a different statistics of the channel in terms of reliability at the lower and the higher frequency. So I would say that when we go at very high frequency, terahertz or millimeter wave, then we can simultaneously ask for high rate, high reliability, and low latency, because there could be an all or nothing effect, that either you get a very high rate or you don't get anything. But at the lower frequencies, you have, of course, to decrease the rate, because also the available bandwidth is lower, but it's inherently more unpredictable, I would say, because it's simply based on looking at the entropy of things. So if I have a range of 1 kilometer, then any obstacle within that kilometer could affect my propagation and contribute to it. But if the signal can only reach a couple of meters, then the number of factors that can affect its propagation is lower.
Yeah, so there might not be a clean answer here, and I suppose it also depends a lot on if you want to cover a small region where you essentially know where your device are going to be, or if you want to cover an entire city, and what resources you have in terms of actually deploying things to achieve higher reliability in that part of the network phase. Or
yeah,
if
indeed,
you...
I mean... Yeah, I mean, like using spatial diversity, this is a sheer fact that the wavelength is longer at low frequencies means that if you want to use spatial diversity, then you need more space for your antenna array, right? So there are many factors that interplay here. It sounds like an interesting research problem to figure out. I mean, given some set of boundary conditions, what is the optimal carrier frequency to use in order to minimize the latency or maximize the reliability for some given latency target and so forth.
And certain
interesting
rate,
perspectives
certain rate
and a certain rate, and maybe or like a certain number of bits, right? I mean, if you just want to get a single bit across, that's a different game to play than as opposed to you want to get a gigabyte or something across, I suppose. So that's an interesting perspective, and maybe something that seems a bit unexplored.
And what I would also add to this is another thing. Maybe the propagation people have already started to do something in this direction, but the fact that if you have a longer propagating wave, then the resulting signal has a randomness and, let's say, entropy contribution from a larger environment. So the unpredictability has to be higher compared to signals which are propagating within a low region. How to formulate this?
Rigorously, yes. Wow,
yes.
Interesting. New research problem, perhaps. So, because there are so many different boundary conditions one can impose here, right? I mean, in addition to bandwidth and power and all that we have in classical comms theory, now we might also have factors like what does the environment look like, how much physical space do we have available for the aperture that's going to constitute our antenna array and so forth. Very neat indeed. Yeah, so there's a final thing that we'd like to talk a little bit more with you about, and that we have only touched upon very lightly, I think, and that is the concept of multi-connectivity and interface diversity. I think something that you have also worked and published on in your papers, Petar. So my understanding has been that the purpose here is to let the device connect with multiple access points or even multiple standards at the same time. So for example, it could be connected to like Wi-Fi, and at the same time it could be connected to 4G or 5G, and then in the future 6G. Is that a correct understanding? And do we need this? I mean, isn't 5G going to be enough here now with all this technology and all these new methods with grant free and slicing and so forth?
I think I tried to have an opportunistic look into these multiple interfaces, in a sense that, our phone, the phone that we carry in the pocket, has several wireless interfaces, Bluetooth, Wi-Fi, cellular, NFC, and so on. And the thing is that if we go to the very basic definition of a communication channel in information theory, is that the channel is a part of the system that you are unable or unwilling to change. So the channel is something that has been given to you, and do the best you can with that. So if I'm information theorist standing on top of multiple interfaces, where one is Wi-Fi, one is Bluetooth, one is cellular, and so on. So I would say, okay, let me define my communication channel on top of this. Let me define what a channel use would be, and let me do a coding across these channels to see what I can achieve. So it's kind of how can I opportunistically use the interfaces which are there. The second point is that even if the appearance of 5G doesn't mean that our phone is going to remove Bluetooth and Wi-Fi, because they all have their use as well, right? The point is that if you have an application which is within a short range and you would like it to happen with high reliability, then maybe why not to use all the interfaces simultaneously if they are available. Another point is that we try to think, especially us communication theorists, within a single system perspective. So we have our model of a channel and antenna and so on. So we want to achieve something with the best possible under some constraints. The thing is that in reality, it might be cheaper to add a new Wi-Fi interface compared to adding many more antennas, at the device. So then the question would be, with instead of having N antennas, I have M antennas, and I have an additional interface. How would I use this system when I integrate them at the link layer? So the integration is not happening, of course, at the physical layer. It's happening at the higher layer. So I think it's just a different perspective on the available communication channel and the possibilities you have with it. I'm not insisting that we always have to build systems with multiple interfaces, although the highly reliable systems like airplanes, for example, as far as I know, they have 3 different communication systems for intra-plane communication, which are redundant, and they are supplied by different suppliers, by different producers, so that if there are some even errors in the software, we do not want them to appear in all 3 systems. So we have 3, let's say, independent suppliers of internal communication cabling.
And that might be the key word here, right? I mean, obviously, being connected to multiple interfaces and so forth makes a great deal of sense from a reliability perspective, but I think the key word is really independence, because if you think about it, if you got like 1% outage on one of your connections and 1% on some other connection, well, if the connections are independent and the combined outage, I mean, the risk that you have outage on both of the connections is like 1% squared, which is like 0.01% or something, right? But the question is, in wireless, will we have that? I mean, if you have like poor cellular coverage, perhaps it is because you went down in the basement and there your other link, whatever that might be, is also poor. I don't know.
Yeah.
I guess that would have to be taken into consideration here, right?
Yeah, exactly. So we cannot offer this high reliability absolutely everywhere. Of course, there are points where this will not be offered. But the point you made there is actually very important, that you're saying that if they're independent, and even if the reliability of one system is only 1%, that means that if it's independent of the other system, it's going to improve the reliability for 2 orders of magnitude.
Yes, right? If it is independent.
If it is independent. But you have to see at other factors here, is that the 5G base station, which is nearby, if that fails because of, I don't know, power supply or whatever, then if you have another system connected to something else, to some other access points, is going to sustain, right? So I think in that sense, with this densification in 5G, putting multiple access points, multiple base stations, it's kind of contributing to this improvement.
Right, multiple base stations or access points that perhaps are operated independently, like they have their own power supplies or backup power supply backups rather. And this, I think, also illustrates one of the most important points that I think you taught and highlighted for me in this conversation, namely that it's easy for, like, say, comms engineer to think about latency as being about avoiding the fading dips on the wireless channel, right? But in the end, latency and reliability are about so many different things. Avoiding the fading dips for sure, but also making sure that, well, the equipment doesn't go down, or some software doesn't crash, or some buffer doesn't get overflowed, or things don't take too long to process, and so forth. So it's indeed a very rich topic, this whole field with latency and reliability when you really see it in a system context. Emil, what do you think?
Yeah, I have one last question, which also sort of connects this. Whenever we have these really complex problems that are hard to optimize all dimensions at the same time, then machine learning appears as sort of our savior. At the same time, Yeah, you were mentioning machine learning as a tool that could be used here, but I get a bit afraid of machine learning for reliability perspectives, because you sort of collect a lot of data and then you try to design algorithms or behaviors that are based on that data. And of course, what stands out in data is what happens most of the time. And most of the time your network is anyway going to be stable. So the reliability just happens in atypical cases. And I suppose when it comes to connected cars or self-driving cars, you need to drive around for so many millions of hours in order to collect those typical situations where you will run into a crash situation or something like that. So if we will use ML protocols to help to get better reliability, how do we really do that to not focus on the typical cases that they're already able to handle, but the problematic cases?
So I think the machine learning, let's say the statistical machine learning, is fundamental to the problem of reliability, because when we say, for example, that we have a probability of 0.99999, that means that we actually know some distribution of our system, and then we design our system to come to that 0.9999. But this is a very strong assumption. How do we know this distribution? And the only way to know this distribution would be to collect data in the environment where you are. So this is not about model-based versus data-based design. We simply need to have the data for the place where we are in order to start to predict the reliability. So I'm now speaking about purely measuring the reliability. There is another problem of using machine learning to run the protocols, to run deep neural networks and so on. So I'm just speaking about the very problem of reliability. So think of the following, that let's say that you deploy a base station and then you put a mobile phone at one spot. And this mobile phone is collecting data for a long time, days, billions of samples. Then this mobile phone is going to get a pretty good model of the environment. And then it can predict that if it sends with a rate of certain amount, then the probability that the packet is going to arrive is certain amount. This is the fading and so on. What is the distribution? And these parameters. Then the question is, how can we predict the performance if we do not have infinite time to collect billions of samples? And there are a couple of interesting ideas there. One is what we are working with my group now is some Bayesian approach. So we are trying to have some prior on the probability of on the reliability, because you can think that this reliability that you are getting at given point is a value you want to predict, because machine learning is about trying to predict something at a new input point, right? So I give you a coordinate, I give you a new coordinate, and I'm saying I'm going to deploy my device here. What will be the reliability there? So I can try to predict that using machine learning, right? And to do that, there are multiple ways. For example, you can have a certain prior, and then just collect several samples, and based on these samples, predict what should be your reliability there. On the other hand, communication protocols are agile in the sense that they do not need a definitive value. They can actually make the protocol, adapt the rate retransmission, and so on to achieve target reliability if they know something about the statistics that is happening in that environment. So another way would be to use certain form of meta learning. And my favorite example there is that you have industries that are running factory automation. Of course, they have different setups, and they're in different countries maybe, and so on. But there is some semantic similarity between them, right? So in a sense that they assume that there is a common prior there that they can jointly train and then benefit from that to adapt to the task at hand, which is within their factory. So this is leading to interesting, I would say, maybe future models of wireless systems and operators, where you have some micro operators that have a very good knowledge and very good models for certain type of environments, and they are going to calibrate your control algorithms and transmission algorithms to offer you high reliability. And this is specialized knowledge based on collected data elsewhere. So this is the use of machine learning for the statistical part, guaranteeing reliability. Then you have the use of machine learning within the communication protocols themselves, which are very complex and so on. And we have seen tons of works on this, how to put a neural network to, for example, do scheduling, slicing, and so on. And these are all interesting works, and they are addressing the problem of complexity of devising these algorithms. And we can decide to use them or not, because we could do a simple heuristic algorithm and so on. But for the machine learning part I was telling before about predicting performance, we cannot decide not to use it, because we must use it to predict the performance.
Yeah, and I guess from a monitoring perspective as well, if you notice that sometimes you are not satisfying your reliability requirements, well, then you collect that data into a data set and you try to sort of deal with those situations in some way as well. Yeah, so that was everything I had to ask you. Do you have anything else, Eric?
Quite amazing. I mean, so many, or rather that there are so many still uncovered and unsolved research problems in this field. I think we covered it all, and it might be time to close up here. So with that, it's really great to have you, Petar. I learned a lot, and
thank you very much for the very, very interesting, provocative questions. Some of them deceptively simple, which made me think of things I didn't really think before.
Yes.
So thank you very much, Eric and Emil.
Yeah,
thank you.
Thank you very much for joining us and sharing all of your nice thoughts about how to build this type of systems and how to really not go beyond just the simplest ways of doing the math, but also thinking more carefully about how do we design things and why do we design them.
Sounds good, Emil. Thanks a lot, and see you next time. Bye-bye.
Thank you very much.
Bye.